This is what Nvidia's Grace Blackwell looks like on the inside, the 72 GPU system that's seen soaring sales from the likes of Microsoft, Google, Amazon, and Meta. But what we're really at Nvidia for is an exclusive first look at this, Vera Rubin. Nvidia's next rack-scale system for AI data centers has the AI world buzzing because Nvidia says it'll help solve the biggest bottleneck threatening AI build-outs today, energy.
It's actually going to be about 10 times more performant in terms of performance per watt compared to Blackwell.
So how did Nvidia pull this off? We're taking you on a deep dive inside Vera Rubin to find out, because this AI powerhouse takes a lot more companies than Nvidia and a lot more parts than these GPUs.
It's not comprised of just chips. It also has the compute trays, the chassis, the side rails, the bus bars, and 1.3 million components, over 80 different suppliers, and across more than 20 countries.
Vera Rubin's in volume production today with plans to ship later this year. But from a memory shortage to a supply chain ridden with tariffs, what are the risks Nvidia faces to getting these 2-ton systems out the door?
There is that risk that with all this AI CapEx, you basically have pulled forward or have a little bit too much than you need, but I don't see that as being a risk this year. And I think that's why Nvidia is so confident that their customers are saying we need more, and if we had it, we could deploy it right now.
From compute to connectivity to power, we take a look at the astounding ecosystem behind this single system and asked Nvidia how it built this complex web and whether competitors like AMD could ever catch up. When Nvidia released its current Blackwell rack design in 2024, demand was insane. Nvidia stock is up more than 100% since before it was announced, because it completely changed the game.
Because it was the first full rack scale design that took this approach of disaggregating compute, the scale of networking, as well as all the memory infrastructure, but all of it was done to make it behave as a single GPU.
The first generation of compute, you'd buy a server, you'd buy a switch, you would maybe buy a rack to cool if you got to a point where it needed that. You got all these systems pulled together into a single rack built for absolute greatest efficiency and greatest performance. And that's just not how servers were historically built.
Grace Blackwell has 72 GPUs, nearly 800 other chips, 1.2 million total components made at some 350 factories.
TSMC is developing the silicon and the core chips. We're working with Foxconn on a lot of the other rack assembly components, Delta Electronics for a lot of the liquid cooling elements. The nozzles that connect on the end of the hoses are made by a number of different providers.
Whether that's Amphenol and getting the connectors and the copper, whether that's Vertiv and getting the cooling distribution systems.
With so many components, not every rack is touched by the exact same global suppliers.
From China to Israel to Mexico to the US, Vietnam, Thailand.
So Nvidia created a standard reference design.
And so the whole idea by creating a standard is it opens it up to the entire ecosystem.
There's power shelves by Megme, Lite-On, or Flex. Power components by Infineon, Analog Devices, or ST Microelectronics. Chassis by Foxconn or Interplex. BizLink for bus bars. Pinda for rack manifolds. Cold plates by Aorus, AVC, Boyd, Cooler Master. JPC to Rico deal for power whips. The list goes on.
This supply chain has really become this core group of companies that are building this all together. And of course, they're all leaning in on the success of Nvidia.
Is Blackwell still sold out?
Blackwell is in full production still. We're still, producing thousands of racks per week. And so what I'll say is they're spoken for.
So now, Nvidia is making the next big leap to Vera Rubin, with full production announced at CES in January.
This is a Rubin pod, 1,152 GPUs in 16 racks.
With about 100,000 more components than Grace Blackwell, Vera Rubin uses about double the energy, but can deliver way more compute.
The number of tokens it's generating is exponentially higher than last generation, and so they've become very efficient for these, these heavy workloads.
To get there, Nvidia redesigned all 6 of the core chips.
So this is our Vera CPU. It delivers about 2x the performance per watt compared to our previous gen Grace CPU. Then of course there's the Rubin GPU. This can actually deliver about 50 petaflops of AI performance, so about 2.5x performance.
So let's take a deeper look at one rack. It has 18 compute trays, each one starring 2 Vera Rubin superchips, the computing hearts of the system. Each has 1 Vera CPU, 2 Rubin GPUs, and much more.
So this particular superchip has 17,000 components. And as you look at all these elements that have to connect to each other, a lot of these are just to help make sure that the power is being modulated correctly. These are actually the SOCAMM memory. So we actually have memory units that can be applied and removed on the new Vera Rubin processor compared to the Grace Blackwell. They were all sort of soldered in.
But the real memory star lines the top and bottom of the Rubin GPU itself. 8 stacks of the latest high bandwidth memory, HBM4, by the likes of SK Hynix and Samsung. Is there any risk because it is in such short supply right now?
The one thing that we've been very laser focused on is making sure our entire supply chain is aware of not just sort of the design itself, but we're actually giving them very detailed forecasts. We're aligning to make sure that everything we're shipping will be met by our supply chain. So I think we're in good shape.
Another risk factor, those 1.3 million components running workloads 24/7 generate a lot of heat. Some customers reported overheating issues in the early days of Blackwell deployments at the end of 2024.
Every component has to fit together perfectly. And I think when we were doing some of those initial deployments, there were things like you didn't get proper seating with the liquid cooling valve. It was just actual implementation, user error. And for the most part, all of the systems are fully deployed today, running hundreds of thousands of scales and without an issue.
Vera Rubin compute trays have no hoses, cables, or fans. It's NVIDIA's first system that's 100% liquid cooled. Will this mean that data centers have to have a really robust liquid cooling loop ready and in place before they can move from Blackwell to Vera Rubin?
Yes, essentially we're requiring, as we build out the AI factories of the future, that the vast majority will be leveraging this liquid cool based architecture.
The superchip is covered with cold plates, piping in water that keeps the components cool.
This is the cool cold plates on the Vera CPU. You also have the Rubin GPUs that are also underneath there.
Data centers currently consume a lot of water. Will Vera Rubin help with that?
One of the counterintuitive savings is actually you use less water using liquid-cooled systems. The main reason is because you don't use the evaporative cooling technologies as much, and that allows you to consume much less water through a closed-loop system.
A lot of the needs for cooling come because of just how much power is running through the system.
It's about twice the amount of overall power, roughly about 220 kilowatts per rack. And so we had to redesign, obviously, the power delivery system.
But most of all, efficiency is tied to how quickly each GPU can access the memory and processing on every other GPU simultaneously, which NVIDIA solves with its own networking product, NVLink.
This is the NVLink switch chip, responsible for connecting all of these GPUs and CPUs together to have them behave as one. So this actually doubled the line rate from again, 1.8 terabytes per second to 3.6 terabytes per second.
9 NVLink switch trays sit between the compute trays, connecting all 72 GPUs together and pushing data at an incredible 260 terabytes per second.
And they connect through this NVLink spine on the backside, and this is really the magic of this full rack scale system.
One of these spines stands vertically, glowing through the back of each rack, connecting everything together with 5,000 copper cables, 2 miles worth.
Each wire specifically placed and aligned to where it needs to go to connect to another connection point on the spine itself.
Finally, there's Bluefield DPUs for storage and security, and outward-bound ConnectX-9 networking controllers, originally built by Mellanox, which NVIDIA bought for nearly $7 billion in 2020.
That was one of the most incredible acquisitions as you're starting to scale AI factories from single systems to full-on data center scale workloads. The networking is incredibly important.
Thousands of racks make up what CEO Jensen Huang calls an AI factory. So how do they all connect together? With entirely separate networking racks filled with NVIDIA's latest Spectrum X switches. Overall, a Vera Rubin rack weighs nearly 2 tons and has about 1,300 chips with some 220 trillion transistors. Still, it's simpler than the current Grace Blackwell system.
You can now disassemble this full compute tray in seconds. Wow. So just what I just did there, to do this with Blackwell, this would actually be soldered to the board. You would need screwdrivers, you would need all sorts of equipment to take that out. And that's why when you look at this complete compute assembly, instead of 2 hours on Blackwell, can be done in 5 minutes. Just push it down there, and now it's inside, wow. Right?
While Vera Rubin is less complex, it'll cost customers more up front. Nvidia doesn't share rack pricing, but analysts estimate the price will increase about 25% from Grace Blackwell.
So from somewhere around 3 to 3.2 to 3.5 to 4 million a rack.
The cost per token is about 10x lower for Rubin compared to Blackwell.
I mean, that's what I hear on my end is matters the most, is the equation of how many tokens per watt or per power consumed can you get. And the more you can tweak that or move up the curve, the higher the return would be on the dollar you spend.
Are there parts coming from China that are constrained because of tariffs? Have you seen prices of certain parts go up, for instance?
So what I'll say is when you look at this supply chain this complex, it's a game of whack-a-mole. And in terms of pricing, certainly given the demand, different components have definitely been impacted. But luckily, given demand, there's also incredible value in making sure that we can secure that.
Nvidia has also been part of the big reshoring push. It's vowed to manufacture up to $500 billion of AI infrastructure in the US through 2029, including making Blackwell at TSMC's new Arizona fabs. Assembly, where all the components are pieced together, often by robots, also happens in the US, and elsewhere, including Taiwan and at a big new Foxconn plant in Mexico. As Vera Rubin starts shipping in the second half of 2026, customers won't need to phase out Blackwell.
This is one of the few times that you'll hear a CEO tell its customers buy less, right? So we really want our customers to buy with our annual cadence because each architecture is going to continue to leapfrog itself. We assume that there will be customers who will be parking Rubins right next to these Blackwell systems as well to power different workloads.
Later this year, Nvidia will see some big competition when AMD ships Helios, its first rack scale system.
You're going to see a lot of uptake because customers want more capacity, but they also want a viable second source to kind of keep Nvidia honest, so to speak.
I don't know if we're the only company that can do it, but I can definitely say that there's a lot of, sort of growing pains that went into understanding the complexity of delivering this type of system that has never been designed before at this scale.
Major Nvidia customers are also making AI servers with their own in-house silicon. We visited an AWS data center in October filled with Ultra servers made up of 64 AWS Trainium 2 chips. And Google's filled its data centers with racks of its own tensor processing units too.
Amazon is developing their own AI chip, so is Google, so is Microsoft, so is Meta, and still they're choosing to continue to work with Nvidia generation after generation. And I think that's a testament to the fact that these platforms that they're developing are very powerful.
Nvidia showed us a prototype of its next big rack architecture leap after Rubin, Kyber, with 288 GPUs.
If you think about the math, we went from 72 to 288, that's 4 times, but the weight only went up by about 50%. And the way we were able to do that, we actually removed a lot of the cabling. What the actual production version will look like maybe a little different, but it's just an example of how we're looking to kind of push the bounds in terms of compute density and overall performance efficiency.
Nvidia's next system, Vera Rubin Ultra, will be available with the Kyber rack design, expected to ship in 2027.
Ultimately, that's where they're headed, is to have fewer connection points, fewer points of failure, more integration. Not only does it make the system faster, but total cost of ownership should go down.
Really, if you're able to pack a large number of components within the same rack, that means that more GPUs can have super low latency. If the user experience of using AI is amazing, then more and more people will use it and they'll use it more. And then at that point, then the demand for GPUs is going to be even more.